First of all, thank you very much for organizing this and for inviting me. My name is Xun Zhang. I'm faculty and medical physicist in the radiation oncology department here. I'm going to switch the topic from the image processing to radiotherapy treatment planning because this is the area that I've been working on. And also I felt this is an interesting topic that may or may not be familiar by the audience here, but I think it's a interesting topic, and I think it shares a lot of similarities in terms of technology with what has been used in image processing domain. So that's why I chose this topic, and I want to also share with the audience here about our progress and get advice from the experts here. So I'm going to present a few topics. First, because I think most of the people here are from the imaging domain, so I'm going to briefly introduce radiotherapy and the treatment planning top problem itself. And then I'm going to cover a few topics in this area where how we approach this problem, how we try to build the models to do the decision making for physicians, for planners, and for the physician planner as a team, and then how human AI interact together to get this problem done in the clinical setting, because the interaction is between human and AI is an important component of that. So finally I'll conclude on my talk. So let's get started. So in the radiotherapy, it's a very, very quantitative field where we actually use image guidance to precisely administer radiation to the target to treat the tumor, while at the same time to spare the dose to the normal organs. And with that, a very generic domain is called image-guided radiation therapy, which covers the following steps. The first thing is we do a simulation where we bring in patients and build a computational model, sort of three-dimensional computational model of the patient. This is done in the very patient-specific way, and we do this in a routine setting where we treat about 4,000 patients at Hopkins per year, and we do this for every single patient. And once we have the three-dimensional model built, we actually put the patient into the computer and do the so-called treatment planning process, where we first delineate, say, this is the region where we need to give certain dose to because it's tumor. This is the organ that can best tolerate a certain amount of dose. So that's a delineation part. And after that, that's the topic where I'm going to talk about the treatment planning. How can we come up with a plan? Like the plan means the order to order a linear accelerator to execute the radiation, to deliver the radiation to the patient based on the patient-specific anatomy to meet the treatment plan, treatment intent. And in this process, I'm going to elaborate more about the requirements later. And once we have the plan done and we call the patient back, put the patient on the table, and then do another imaging, typically CT, and these days MRI as well, to really image what is the position of the patient at the moment of treatment. And based on that, we adjust the patient position, and finally we can deliver the radiation as we planned. And the radiation we delivered should precisely match what we planned in the second step here. And this process may repeat. As I mentioned in my talk, I'm going to focus on this step, the treatment planning step. So first of all, before I talk about the details, so what are the treatment planning? What is the treatment plan? So essentially, there's a series of control parameters, that are very complicated, complex list of parameters, including thousands of parameters, that precisely can be used to control the status of a linear accelerator. We input that parameter into a linear accelerator. The linear accelerator will execute it, deliver the radiation. Conversely, we want to find out what is the parameter that is needed so that we can deliver the radiation to the patient. And this has to be done based on patient-specific anatomy, because the same radiation given to different patients, the dose distribution will be very different, and because the specific radiation interaction with a different patient anatomy. So with that, there are actually two objectives as we develop a treatment plan. The first one is deliverability. That means the plan, whatever we come up, the plan has to be executable, has to be deliverable by the LINAC. Otherwise, the plan, even though it's no matter how good the dose will look like on the paper, it cannot be used in the clinic because it's not achievable. And because of that, that means the plan has to meet a certain linear accelerator hardware constraints. For example, how fast the machine can move at the most, how fast some component of linear accelerator can respond to certain changes, etc. So there's a long list of a requirement about the deliverability. The second is more complicated, which we call it acceptability, because the plan quality has to meet both dosimetric requirement guidelines established by the national standard, as well as by the physician's preference, because usually national standard just sets the bare minimum requirement for, say, we treated this patient this way. But on top of that, each physician may have additional requirements and considering the history of the patient. For example, if a certain patient has impaired lung function in one side of the lung, we need to consider the dose to that lung as we do the treatment planning. So these two are coupled objectives as we have to meet both in the treatment planning process. And then the question is, what is the current standard status and why we need improvement? So I'm just outlining the current treatment planning practice. Essentially, there are two steps, two loops. The first one, we call it planner TPS, treatment planning system interaction. Treatment planning system is a software system where basically it solves optimization problem. So we define, say, this organ can receive this much of dose, this organ receive that much of dose, and then we give that order to a software. The software will run the optimization, come up with a list of plan parameters, and we see a plan. And the planner has to sit in front of the computer, try to tweak these priorities of the plans to come up with a plan that is best meeting the plan quality desired by the planner. These planners are not necessarily physicians, so at this moment, the plan quality is only meet the planner's expectation, but not necessarily the physician. Of course, the plan generated this way meets the deliverability condition because it's done by the software. The software already consider all the hardware limitations. So that's the deliverability aspect of the consideration. To put this in the context, we are talking about 20, 30 parameters to tweak for each patient, and the experienced planner sits in front of the computer, tweak these parameters, try to come up with a plan. And as you can imagine, this is very similar to as we tune the hyperparameter as we develop a neural net, try to make sure it's learning something that as we planned. So that's very similar, and this is just a routine work for our dosimetrists. The second, once we have a plan done, and this planner will verify that with the physician, because the physician is ultimately ordered to say this plan is good or not. And that's where the physician and the planner interaction come from. And then they will talk and they will exchange ideas. If something needs to be improved, the physician tells the planner to go back, make changes. This addresses the acceptability component. What is the problem in this process? So first of all, the plan, as you can imagine, this is not about in research setting, we try to push for the best result for every single patient. This is routine. We are treating about 4,000 patients. We have 20 dosimetrists in our clinic. There are substantial amount of quality variation because a lot of times we try to get plans done on time. And the plan substantially depends on the planner's experience, available time per plan, as well as how well the planner and the physician to talk, because it's not easy to get physicians available during the routine clinical hour. There's also very low planning efficiency. Right now, it takes about a week for us to complete a plan following our clinical standard, and this lengthy planning time also compromise the treatment outcome for some, for example, some tumor type that grows very fast. And of course, there's a very high healthcare cost. There's the cost of staffing, there's the cost of training and education, etc. So we really need a change to this standard clinical workflow. It's not about TPS cannot solve the optimization problem. It is about how do we know what plan needs to be achieved and how to get there. So I'm going to talk about the next a few topics about what we did to attack these problems separately. The first one is very straightforward dose prediction. So once we have the neural network, a very straightforward application is to say what is the best dose that we can achieve for a particular patient, because the best dose depends on the patient anatomy. And that's a very typical image processing task. We set up a network, input anatomy, get the dose done. That's very straightforward. A lot of successful work has been done there. And outstanding results that can be achieved. Say, this dose can be used to guide the treatment planning process. But the challenge is this result only tells you what the plan should look like. It doesn't tell you anything that this plan is achievable by hardware or not. It just tells you this is the best plan. And further, this best plan may not even be realizable. It may be only good on paper. And then the next approach in this category is how can we predict physicians' preference in terms of approving a plan, right? Once we have a plan get presented to the physician, whether this physician will approve it or not. And if you have that score can be used to guide treatment planning. So that's the next, another set of the story in terms of plan approval. And of course, when I studied this problem, I started to do literature search, and not surprisingly, the problem has been studied a long time ago. In 1996, this group used a neural net. At that time, only one layer of neural net, try to predict, say, what is the features in the plan that the physician will decide the plan is good or bad. And that was very, very innovative at that time. And of course, with one layer of neural net, you cannot expect the plan approval quality is good enough. But overall, the direction is very interesting. Along the same direction, we try to build the so-called virtual physician. So we use a deep neural net as a universal function to approximate the probability for a plan to be approved. In other words, we have a network, input a plan, and output say what is the probability for this plan to be approved by this physician. And this is it's a relatively easy problem if you were to have both good plan and bad plan, because you can treat it as a classification problem. The challenge in our clinic is we don't only have good plan. All the bad plans has been discarded in the treatment planning process. We never store them, or very rarely we store them. So what do we do? And then to overcome this problem, essentially we try to do the adversarial learning in this process to generate a bunch of plans, and we consider those plans are not accepted in this process. So it's a very straightforward application of adversarial learning. At the end, we can train this neural net to predict the plan approval probability as we using only approved plan data. And this is the test showing that this is sort of a classifier can distinguish the approved plan and bad plans in the tests. And the same idea also applies to the HDR brachytherapy. This is a subdomain of radiation therapy that uses radioactive materials instead of external beam radiation, but the concept is the same. More importantly, we can look at say among the feature domains. So what are in the feature domain where the probabilities of approval clustered? So only at a sweet spot we see that the plan is approved by the physician. But as we deviate from the sweet spot in certain directions, there is the plan approval probability start to drop down. And more importantly, we can see the trade-off. Say the physician is willing to sacrifice this organ by 3% to gain another 2% of the other organ. So that there's a trade-off that buried in the physician's mind to make a decision about plan approval probability. So that's the first side of the story about how we can do what we did to decide to mimic the physician to decide what the plan whether the plan is good or not. And we can imagine this information can be used to guide treatment planning. The second aspect is to make a decision as a treatment planner in terms of operating the treatment planning system to come up with a plan. Again, as you can, as I presented in the previous few slides, the typical work for the planner, the dosimetrist, is the planner will sit in front of the computer, look at this interface, and think, what should I do to improve the plan? And if the plan is good, of course, we are going to get a plan. If not, the planner decides, okay, I need to change certain parameters, like how we tweak the hyperparameters in building our deep neural net. And then we adjust the parameters, we launch the treatment planning optimization one more time, and we come up with a plan, and this loop continues. This is, to us, very like playing a computer game. And because of that, we, in a few years back, remember, in early work that DeepMind demonstrated that actually reinforcement learning can be used to control computer to play computer games. Without surprise, we think we can do this in this process. We can build a virtual planner in place of a human planner to get this done, as long as we know the planning score. Because when you play computer game, you know what the score should look like. In this case, we have to have a good score. So without going into detail, we employed a very similar technique, reinforcement learning, to get this done. And in reinforcement learning domain, we have to, our goal is to build the top virtual planner, which is a neural network. And this virtual planner takes the input of the state, which is the plan in this case, and come up with a decision what to do with this plan in terms of treatment planning system, and feed this action to the treatment planning system, and let the treatment planning system to take care of the optimization part. And in this process, the training is done by going through this loop again and again for the planners to discover what is the best strategy or policy to operate the treatment planning system in terms of treatment planning. And of course, it's more complicated than that. We cannot build the virtual planner using a very simple network. It's a very complicated decision-making process. So we build the hierarchical decision-making process motivated by how our human planner is doing treatment planning. When we stare at the computer, our thought flow is which organ needs to improve, what parameters for this organ needs to be improved, increase or decrease, etc. So that type of thing. So we build 3 sequential networks to allow us to mimic this human decision-making process in this virtual planner network. And that is how we train this, how we build a network, and it also solves the problem of scalability, because now as we move to different tumor sites with many organs, the decision or actions that we need to decide will explode very rapidly. So we have to have a scalable network to manage this problem. And then once we have the network, the next thing is how do we train it? Of course, reinforcement learning idea is to train by exploration, let the network to explore different actions and remember the best and forget or penalize the bad outcomes. But that doesn't work because the knowledge or the action space is huge. To further improve the training efficiency, we build the knowledge guidance. So basically, we have a dosimetrist to write down like what is the typical strategies that a human dosimetrist will do, and we use that to guide the training process, but still leave the room for exploration so that we are not limited by the prior knowledge. This way, we can try to balance the learning efficiency as well as the advantage of deep reinforcement learning to explore unknown strategy. We really hope this virtual planner can come up with some novel strategies that hasn't been discovered by human, and to get good plan done. And of course, last is GPU processing. So the one bottleneck to get this done is to interact with the commercial treatment planning system. The commercial treatment planning system is not intended for doing this, and it's super slow because, and we are talking about thousands or 10,000s or even more times of optimization. Repeated optimization. We cannot afford it in this task. So we actually build a GPU-based treatment planning system in-house to mimic the commercial system. Of course, with some difference, with some simplification, but this in-house software can be used as a starting point to train our network before we couple with the real treatment planning system. So with this, we get some initial success. This is one of the early phase cases where we try to plan a prostate case. In the middle is a prostate cancer. The goal is to give enough dose to the prostate, the round-shaped organ. At the same time, reduce the dose to a urethra, which sits in the middle of the prostate. So from the left to the right, that's the sequential steps when we have this virtual planner to do plan by itself. In the first step, it comes up with a reasonable good plan. In the iteration number 5, it started to confine the dose to the prostate, so that we can reduce the dose to rectum and bladder nearby the prostate. And in the 13th iteration, it started to purposely reduce the dose to urethra in the middle of the prostate. And I have to emphasize that I didn't tell this computer to do whatever it needs to do. This is all discovered by the computer itself. So we are very happy about this outcome. And to test it, so we applied this virtual planner in 2016 planner challenge. So this work was done in 2022. But the competition is held by the medical dosimetry world. So they have this worldwide dosimetry challenge every year with human dosimetrists to compete who can do the best plan. And this case was a retrospective study that was done in 2016. The competition was 2016. So we applied our planner to that case. And this is a real prostate case with 13 structures included. And we were very happy that our planner ranked number 3 among all the human planners at that time. So that's a good, very encouraging result. And then in 2023, we secretly participated in this planner challenge, competing against all the human dosimetrists in this challenge. And this is a much complicated case of head and neck planning, head and neck cancer, so that there are more organs. And it's not the standard treatment planning because it's actually adaptive treatment planning. It competes for what is the best planner. Who is the best planner that can achieve the plan the fastest and while still meeting all the planning requirement. This is a plan that we did, and I wanted to highlight. So at the end, our planner, we won the first place in terms of achieving the fastest overall time using our software, iPlanBot. Of course, we didn't tell the organizer we were a computer robot to get this done. And the third planner I highlighted here, third fastest time, was actually a human planner that was also participated in this process. This is just a comparison between the clinical plan and the virtual plan. So that's the second topic. Now that we separately addressed the question of how to make a decision about plans good or bad, how to achieve the plan using a treatment planning system, of course, the next step is to connect the two to get the team together, to mimic what is really done in the routine clinic. So with this, we built this virtual team. Not surprising, just to couple everything together. We have the virtual planner to operate a treatment planning system, but this time, as we train the virtual planner, the score function is not only the plan quality, but also the physician's preference score that we trained in the first step. And the data is a bit scattered, but overall, what I'm showing here is the comparison between the plan scores with and without using the physician's preference. Without using the preference, that's the red dot. Don't know if you see my mouse. Yeah, that's here. So the clinical plans done by human, those are more scattered, with the plan scores scattered all over the place. But with the human, human virtual physician score, the plans were pushed towards this direction, indicating the plans are more likely to be accepted by the physician. The second plot essentially also shows the similar idea. Basically, by coupling the physician's preference in the treatment planning, we can come up with a plan not only deliverable by the machine, but also more likely to be approved by the physician. And of course, these are all done quantitatively by metrics, evaluated by metric. We also presented to humans, physicians, and physicists to say, given the same patient, a clinical plan that has been done by qualified dosimetrist planner, and also the plan done by us, which plan do you prefer? So among all the three reviewers, they all highly prefer the plan that was done by the computers, not by the clinical plan. And a lot of reason is because the clinical plan was done under time pressure, so the plan was not done to the best quality. I also highlighted at the end, below of the slides, that one case favored by all the humans is a patient with hip prosthesis. So actually, among all the tested cases, there was one patient cases. The patient had a prosthesis. So the human planner knows to avoid the beam angle, to avoid the beam going through that angle. But of course, our computer doesn't know that, so the computer uses that angle. And because of that, all the reviewers were able to figure out that that is not for that particular patient, the clinical plan is good. And one last plot showing that as a standard quality assurance process, we have to run all these plans to a quality assurance process to make sure they are deliverable in the clinic so that we can use them to treat patient. So, and the plans that we generated by the computer, they all pass all the the standard quality assurance process, indicating that these plans are ready to be treated, to be used in clinic. So that's the last step that we have to verify. The last angle I wanted to present is human-AI interaction, because even we have all these plans down, we are confident the plan is good, but still there's a chance that physician wants to make changes to the plan, right? Because physicians are creative, and they may want to say, hey, can I still push this a little bit? The question is, how do we let the physician to do it? If the physician still talks to the planner, there will be a problem, because it's hard to find the planner's time to fine-tune this plan, and a lot of times a lot of tasks has to be redone. So to do this, we actually try to see whether we can leverage some of the language models these days to get some things done. The first aspect is explainable AI. For this, we try to build a network that try to convey to the physician, say if the plan, or convey to the planner if the plan will be approved or not approved. If it's not approved, what is the area that has to be improved? So that we built this network to achieve this goal, and this is just a few examples. I don't anticipate you read all these, but generally we gave the prompt to the language model, say this is the description of the plan. Say this is the plan, the dose to this organ is certain, and please provide feedback on which region of interest do need to be adjusted. And then the response is, okay, the physician will likely to approve this plan, or if not approve the plan, if not approved plan, the dose of certain organs has to be changed. So that's the idea. We have demonstrated this work in the brachytherapy domain, which is a smaller scale of treatment planning problem, but we are extending this to the external beam. And this is a Shipley score to allow us to quantify if the plan is not approved, what is the aspect in the plan that has to be improved. And the second is conversational aspect. So if the virtual planner generates a plan that may not be approved by the physician or needs some changes, what can we do? Again, this is in the brachytherapy domain to demonstrate the idea. So the first step is basically what we have done to generate a plan. And the second step is basically get this plan feed to the conversational robot so that we can talk to the conversational robot about what needs to be done. This video sort of demonstrates the idea.
Virtual planner.eqd2 for CTV is 84.2 gray. Bladder is 106.6 gray.
Maybe it was muted. But anyway, so this is the interface. The interface will say plan is done.
How can I help you?
And waiting for the physician's input. The physician will say, okay, reduce the bladder dose by 20%. And then
reducing bladder dose.
In response to that voice, the auto planner will automatically decide what to do in terms of operating the treatment.
Bladder is 99.5 gray. Rectum is 60.3 gray. Sigmoid is 60.8 gray. Small bowel is 49.7 gray.
Human and AI interaction, we can actually get the plan done. So that's the idea. So with this, I'm going to just turn on the current practice again. This is actually the current practice in our treatment planning world. We have this workflow, kind of cumbersome workflow, but still utilized by our clinical practice. As I mentioned, we have about 20 dosimetrists dedicated for doing this repeatedly every day for 4,000 patients that we treat per year. And this is a huge problem, both in terms of quality, efficiency, and healthcare cost. We really want to solve it. And the fundamental challenge, or the root cause of this problem, is we have a treatment planning system, which is a software. It can know how to do optimization, but it doesn't know what is a good plan. So we need some sort of decision-making to help or to accommodate, to work with the treatment planning system to get the plan done. And then the future is, we envision, is really put everything together, what I presented together, where we have an execution module to operate the treatment planning system, like a virtual planner. We have a decision-making module that can decide what the plan is good or bad, and to mimic a physician, and also a conversation module that can communicate with the physician in case anything needs to be done, in addition to what the automation, what the AI modules learned. And of course, this is just the beginning of I think to me, a very exciting journey, just the beginning work. But there are a lot of works to be done. For example, we have to develop a model considering data quality, clinical translation evaluation, generalizability, interinstitutional variations, and of course, down the road, system maintenance, and last but not least, the liability. If something goes wrong by this problem, by AI, who is liable for that? So with that, I'll stop here. I want to thank our lab members, all the collaborators. Many are sitting here. Thank you all for the great work, and thank you all for your time.
So we have a couple online questions, but I'll keep my eye over my shoulder for any in-person ones. First question, Sandeepan Ganguly. How do we generalize the solution space across treatment sites, stages, and treatment machines? And it's sort of a related, instead of dose constraints, and forgive me, I don't know these acronyms, do you think NTCP, TCP can be used as your objective?
Yes, it's actually multiple questions in this question. So first, the generalizability. With respect to machines, that's easily done because that TPS, because we have the treatment planning system in the loop, that software already considered all the machines as long as we commission the TPS to the machine. So that's easily to be taken care of. Between different body organs, that's quite a challenge. For example, the robot that we train for prostate doesn't work for planning the head and neck. We have tried that. So I think the next step is to generate some robots that can master all the tumor sites altogether, just like a human dosimetrist that they are trained to learn the planning not only for specific site. The last question is TCP and NTCP. Those are the tumor control probability and the normal tissue complication probabilities. Those are established math models to predict treatment outcomes. Yes, we can easily include them in the objective functions as we train the AI models.
Great, thank you.
Very interesting work, particularly the second part about using reinforcement learning for the planning. My understanding is that the action is the parameters, right? And the state is the new training, new planning.
New plan,
and
yeah.
The reward is the mismatch between the previous and the new, right?
That's right, yes.
Okay. Have you tried to use any a new reasoning model to replace reinforcement learning?
No, we have been focusing on reinforcement learning over the years, yeah.
Okay.
Yeah.
So my guess is that if you use reinforcement learning, you probably need to retrain every time you switch to different organ. And I'm just curious that whether you can train any reasoning model, like a DeepSeek reasoning model or Google's deep reasoning model, so that you can get one model for all the organs altogether. I think that's something was even just simply tried.
That's exactly the work that we are working on right now in the group. We try to get like I mentioned, the one dosimetrist, one robot that can plan all the tumor sites, just like a human dosimetrist that don't have to specialize in any tumor area.
Okay, another online question. This is from Ergis Subashi. Great work, thank you for sharing. Can you comment on the process that should be implemented for acceptance and commissioning of AI-based treatment planning systems?
So if you talk about like clinical acceptance, we haven't gone that far because that's a whole series of approval and get people's buy-in, etc. There are many things to talk about that. So far, we have only tested in the research setting. Like we have a plan and we try to compare the plans between the clinical plan and the AI-generated plan and have that reviewed by the physicians.
Okay, thank you. Could you comment on how fast all these AI-based treatment planning need to be? Some of the applications probably not that sensitive, time sensitive, but some of them are really need online adaptation, other things that really to be very fast. So could you comment on that speed?
Right. So as you mentioned, it really depends on the context. For routine planning, right now it takes a week for us to do a plan. That's still acceptable. not desired. We want to really shorten it to 2 and 3 days, if possible, or even less. And the big hurdle in current planning process is because it's very hard to engage physicians. They're all busy every day. Even we have a plan in the morning, we send it to the physician. They don't have time to review it until evening. So that's a challenge. And by building some of these decision making for physicians, we can best generate plans to align to the physician's mind that can shorten this kind of planning time. For online treatment planning, for example, when the patient is really on the couch waiting to be treated, we need to get the plan done in like 2 or 3 minutes. That's really the challenge. Not only the optimization part itself, but also all the planning, decision-making part. But luckily for that, we do have the prior knowledge for example, how this patient was treated in the day before, and that already showed what is a good plan should look like, and we have a lot of things to learn from there. And I think by utilizing those kind of information, we can really speed up the process in treatment planning process.
Thank you.
Thank you, Shun.
Okay, thank you.